Good frosty morning, everybody. Stay warm. My own growing up in southern Florida instincts are, of course, heavily offended by all of this, but I'll get over it. So I'm going to spend some time today going over issues that came up in the lab yesterday. There were several points that were clearly causing a lot of confusion. And so we're going to spend some time thinking about those and taking any questions you might have. And then with the balance of the time, we're going to talk about Project 4, which we'll be starting today. So thinking about the TriLab, let's go over sort of the overall strategy of the lab and the way to think about the data structure and how some of these different pieces fitting together. So first thing I want to mention is part of what we want to get in the habit of doing is getting familiar with the official Java documentation. So if you can search something like ArrayDeck Java 11, top link that comes up in Google is Oracle Help Center. What does that mean? And that gets you the official documentation for that class. And once you're there, there's actually like a full index of literally everything in the Java library. And you can browse it if you really, really want. I mean, you can sort of keep doing, this is just the letter A. But knowing that it's alphabetized and knowing that you can click to it via these letters creates some possibilities. And there's also the all classes link and so forth. And so you can look up literally every class in the Java standard library, which is kind of convenient. So anyway, I want to just review how I got there, right? So I put in the name of the class, Java, and then the Java version of documentation that I want. For various historical reasons, the results of searches tend to lag a bit. So when I just did ArrayDeck, the top link I got was the Java 7 documentation, which of course they maintain. And they will maintain until the end of time, or the internet, whichever comes first. I'm not going to make a judgment call on that. But in any event, there's a funny little reference. There's this science fiction story by the author of Vernor Vinge. And Vernor Vinge was once a computer science professor. And in this particular story, they're hundreds of thousands of years in the future, and the computers running their starships are still using, some of the source code comes from Unix from 1970. I find that not at all difficult to believe, the way that software tends to persist. In any event, so here we are, ArrayDeck 11. And so we can look at this and we can see, well, what methods does it make available, right? And so we can see that, among other things, there's add first, add last, and then there is get first, get last, and remove first and remove last. So just seeing that those things are there, we can always try to make use of the deck just in terms of thinking about the ends, the start and the end, knowing that both of those operations will be efficient. You can also just think of it as a stack. So it has push and pop right there, just ready for you to use as well. And then there's also add without a qualifier. And it's like, well, what is that exactly going to do? That turns out to be equivalent to add last. So the idea is if you just use add and remove, it'll treat it like a regular first in, first out queue. So you can use add and remove to make it behave like a queue. You can use push and pop to make it behave like a stack. Or you can use add first, add last to just make it, and remove first, remove last, so that you know exactly what it's doing. And any of those approaches are fine, but you just need to be conscious of what you're doing. But in any event, like I said, one of the goals of the lab is for you to really start getting into practice of looking up this documentation, because as you continue to program in your career, you're going to be exploring not only languages you see in college, but other languages. At the moment, I do not teach a single programming language that I learned as an undergraduate. You know, life moved on, the market moved on, I'm doing different things. And within a couple of years, so will you. In fact, there are so many languages and frameworks out there at this point that I won't even hazard to predict what kind of language you might use in your first job. So developing the skill now of getting used to reading the documentation created by the language designers is a really great skill to be developing. Some of the prose is, of course, boring, technical, and at times incomprehensible, but developing a sense of this is what they're trying to say is a really valuable and useful thing. And also what matters, right? Like you look up some library class and it has 20 methods. And there's really kind of an art to scanning over it and getting a sense of this is what I care about and this is what I don't care about. And kind of homing in on that, again, is a pretty useful skill to be thinking about. So having said that particular little rant, let's jump back to the code itself and start thinking about what's the stuff you have to do. And of course, the reason I'm talking about ArrayDeck is that is what find needs to return. And find caused a lot of confusion, considerably more than I anticipated, in fact. And so I'm going to spend some time going over what its role is and what exactly it's trying to do. And I'm going to talk a bit about two distinct strategies for implementing it. And one reason I'm going to talk about two distinct strategies is that in multiple cases, I saw several of you trying to combine both strategies in a single implementation, which typically did not work well. So the two basic strategies then, and I talked about this with several of you yesterday, but I think it'll be helpful to have a summative discussion, is we can take a recursive approach or an iterative approach. So both are valid and legitimate approaches. Both can be made to work very well. There's no compelling reason necessarily to take one or the other. It all comes back to what do you find the most intuitive approach to getting the thing to work. So let's start by talking about the feel of the recursive approach. So remember, what we're trying to do is build a stack of nodes representing how far we're able to dive into the trie to satisfy the prefix that's been submitted to us. So first, thinking about the recursive solution, the essence of the strategy is something like this. If prefix has no characters, this is the base case, is having no prefix at all. If you have no prefix at all, there is no basis for examining the child nodes, right? In other words, you've dived as far as you can dive, right? So if the prefix has no characters, what we would do is return the ArrayDeck containing just this node. That's all. So you just return that. So you create a new ArrayDeck, you push the current node into it, you're done. Now there's another base case. This isn't the only base case. This base case is you run out of string. You run out of thing you are searching. Another base case is you run out of tree. In other words, you're at a node with no children. And you know what? It's really the same thing. So here, why don't I'm trying to do this little two-column thing, so I got to move this around. So if the prefix has no characters, or there are no children, then we're going to return this new ArrayDeck containing this, right? And that's all we need. Otherwise, we both have at least one character in our prefix and at least one child node. Okay? So what we need to do at this point is figure out where are we going next. So again, there are actually two options. So let's think about how we think about the options. What we're going to do is we're going to ask, and we can just throw this in a variable. We could say something like child equals, get child for the first letter from our prefix. So we just look at the start of the prefix, we get the first letter, and we ask our node, what child is this, right? And that returns an optional, because there might be a child that corresponds to it, or there might not be. So let's say there's not. If there's no child, we are really just back to this scenario over here. Otherwise, we finally get to do some recursion. In other words, there are three distinct ways that the recursion can kind of run out of gas. So the else, then, there is a child, means that, and this was something that really confused a lot of you all. When we're doing recursion on this sort of thing, we have to think extremely carefully about which object we're making the recursive invocation on. In numerous situations, I just saw this popping up over and over and over again, somebody would be valiantly inserting a recursive call that was on the same node you're already on, and would lead to stack overflows, infinite loops, all kinds of horrible, horrible things. So the key is that we need to ask, so what we're going to get back is a path. So we're going to get this ArrayDec back from the child. So we're going to ask the child to do a find on our prefix without the first character. Right? So in other words, we just do, kind of find a substring, right? So that gets us back this nice ArrayDec full of everything it found as it explored. And then, we're going to push this onto there and then return it. And there we are. So this is just kind of an outline. There are other ways you can do this. For instance, you might find it easier to kind of process all of this, figure out what's happening. In other words, you might start, you start with, here we go. So you start by initializing one of these. Then, in the course of your if-elsing, you get to this point, well, you just replace it with what you get from the recursive call. And then this path.push this can just happen after all the if-elses are over. In other words, you might not even bother with the return up here. You might just have some if statements that make sure that you only get here if you should. And then at the end, you always just push this and then return it. That's probably even simpler than what I outlined here. So, but again, I want to give you the general idea of it, and then you need to digest this and figure out how to turn it into something that makes sense to you. So that's the recursive approach. That's the overall strategy recursively. Any questions about that approach? Okay, then we're going to talk about the iterative approach next. So in the iterative approach, we don't do any recursive calls. What this means is that we need a variable that's going to keep track of which node we are currently visiting. So the very first thing that you have to do if you're undertaking an iterative solution is set up that variable. So you've got something that looks something like this. So you say something like try current equals this. In other words, you start your exploration of the tree with this. But now that you've set up that current is equal to this, it's time to forget that this is there. You need to be reasoning constantly in terms of what's the current trie node that I'm actively concerned with. And this is largely irrelevant at this point. I know that the puns are overwhelming, but I just want you to forgive me for that. Anyway, the overall scope of the iterative strategy then, in comparison to the recursive strategy. So the recursive strategy, we're constantly just looking at the first letter. And the reason we can look at the second letter is that when we do the recursive call, we shave off the first letter. So we're constantly looking at first letters, but we get through everything because we're constantly shaving first letters. The idea of the iterative approach is to simply use a for loop to traverse the string. So you have something like, for each character in your prefix. So a loop that has that overall flavor to it. So for each of these characters, the question is, well, what are we going to do? So we need to find out, what child corresponds in the current node to the letter that we're currently exploring. So again, I say something like child equals get child for, whichever character I'm looking for, right? And if there is no such child, and really this can happen two ways. There are no children at all, or the child we're looking for isn't present. So if that happens, we're pretty much done at that point. We want to break out of the loop. You can either do a return from inside the loop or use break to exit the loop. Of course, we have to have something to return, which means that we did need to set up our array deck up here. So we've got something to return. So in general, I prefer to do early exits via returns. And so I might say something like return path if there's no child, right? Now, part of the fun of actually typing, right, is when you get ideas about, I forgot that, you can easily go in and edit it. Just drawing like this makes it a little harder. So forgive me, right? Each time through the loop, we need to push current onto our path. Right? So every time through, whatever that current node is gets attached. Because we've gotten to it, it's appended. It means that every edge preceding it is something we've found and matched, right? So, and getting that right is very important for this to return the right thing. Okay, so otherwise, what are we doing? At this point, we have found an appropriate child, which means that we just need to move on. So we can say current is equal to child. And that's the general idea, is we're just trying to navigate the trie to find all the nodes that bound the prefix characters that we're looking for. And notice that once we run out of characters in the prefix, we're done. And at that point, return our path. So both of these are valid algorithms for find. They both produce the same thing in the end, this stack of nodes that were found. Okay? So that's the recursive, that's the iterative. Both are perfectly great solutions. There's no intrinsic reason to prefer one or the other. Any questions about either of these? So, having talked about find, we can now think about add, contains, and remove. So each of these needs to use find. Each of these needs to use find. Phrased differently, you can implement any of these without using find, and in the process, you will have replicated absolutely all the work you did in find. So it's kind of up to you, really. But we're just going to go with you created find. Unfortunately, this stuff is really kind of hard to test incrementally because you can't find anything unless something's been added to the trie, but you can't very much add anything unless you know how to find. And so you kind of have to get both of them working at the same time, which is challenging, but part of just what needs to happen to make the data structure work. So let's think then about contains. So with contains, we're going to get a path by calling find on our prefix, right? And so now that we've got this path, the question is, what kind of information do we need from it? And there's some interesting subtleties here. So let's scroll back to Monday and look at this try over here that had at, ant, barn, barn. Well, it used to have barn, barn, but I think we removed them. Anyway, let's imagine that I do a check for ant. So when I do my check for ant, how many nodes am I going to get back from find? Four. How many? Four. 4 is correct. I'm going to get the root node. Then I'm going to get the node after A, the node after N, and the node after T. Now, ant has only 3 letters. That's okay. We just need to be clear about what we're getting back and how it relates to the thing we're looking for. So if I scroll down here, what the first kind of sanity check is I need to see if I've got the correct number of nodes in my path given the specific thing I'm looking for, right? If I've got the wrong number of nodes, I know that it's not there. When I did find, either I ran out of tree or I ran out of string. Actually, I ran out of tree. When I run out of string, I still get the correct number of nodes back. So if I got the incorrect number of nodes, I ran out of tree. Okay. So that's kind of the first check. So if our prefix length is not equal to the path size plus 1, then it's not there. We can rule it out at that point. So now we know that it went the right distance. And because it went the right distance, the prefix as such is present. The question is, does that prefix actually correspond to a member of the set that we're representing? In other words, if we come back up here and look at this thing, let's say I was looking for the word an, A-N. I'm going to get 3 nodes, which is 1 more than the number of letters. That's good. But when I look at that last node, it's a false. It's not a member of my set. And so I need to return false. Now, if this F happened to be a T, then I would return true. In other words, I just want to return the isMember value for that node. And that node is just on top of my stack. So basically, I'm just returning the path.top.isMember. And of course, I'm not trying to be precise with the syntax here. I'm just trying to get the general idea across. But that's contains right there. Some of you did astonishing amounts of work for contains. It's really not meant to be more than that. So if we can get find working, we're good on contains. Any questions on this? Add is trickier. Now really, once you've got contains working and add working, the rest of this is kind of nice downhill energy. Why? Because you know you've got something that can actually represent your values and you can look them up. At that point, remove, and even the traversals aren't so hard. But add is actually pretty challenging. And the reason add is challenging is that there are just so many different scenarios to consider. There actually aren't that many, but it's more than one. So let's talk them through a bit. So the first scenario is all letters are present in the try. So this happens sometimes. So we can determine if we are in this scenario by checking the length of the path we get back from find, right? If that path we get back from find has at least one more node than the length of the word, and I say at least one because our word might just be embedded in the middle of the thing, right? But if it's embedded in the middle or if it's going all the way to a leaf, it actually doesn't really matter for add purposes. So let's think conceptually about what I mean here. Let's say I'm going to add the word "and" to this try. So I do a find. I'm going to get my 3 nodes. And it doesn't really matter that I could have kept going, right? So I've got my 3 nodes. So in that sense, I've got a match. And now all I need to do is change that last node to true. And it's added. Note the symmetry with contains here. You can't really reuse your contains implementation. Find is the common work that we can factor out of both of them. But we're checking the same kind of thing. You know, if that number of nodes is equal to the number of letters plus 1, then we just look at that top node and we change it to be true. So coming all the way back down here, so all letters are present. Change the path top is member to true. And it's added. So really all we're doing here is we're leveraging the fact that the string is already encoded in the try and we just need to mark it as a member. Scenario 2 is a little trickier. So 0 or a few letters are present. Now, which of these it is actually doesn't matter at all. You're going to do the same thing regardless. Now, what's that same thing going to look like? Well, we need to find the offset into our prefix. So in other words, we need to know how many letters are already present in the try so that we know which letters we still need to add as new nodes. Now, it might be the case that 0 are present, in which case we're going to add all of them. 1 or 2 might be present, so then we're adding 4 or 5 or however many more we happen to actually need, right? So, in thinking about this, calculating that offset is crucial. And to calculate that offset, we just, again, use the length of the path we got back from find. So if I get a path of length 1, it means all I got is the root, and 0 letters are present. So if I have a path of length 1, I am using my whole string. If I have a path of length 2, I'm using all but the first letter, so forth. So in other words, if you put together the right substring call, this is pretty easy to do. So now that you've done this, you can, as before, take either a recursive or an iterative approach to adding the nodes to the tree. Again, it doesn't really matter which one you do, but you should pick one and stick with it, right? So let's think about what those approaches look like. Recursive and iterative. And so these are going to feel a lot like find. With the recursive approach, you're going to be gradually shaving letters off your word. With the iterative approach, you're going to have a variable that's tracking your location in the try. So let's think about the recursive approach first. The base case is if our prefix is empty. So if our prefix is empty, there's nothing to add. So at that point, we set is member to true. So in other words, you're hanging out in the last node that got added. So you flip that to true and you quit. Otherwise, you've got some work to do. So specifically, and note that if you're taking this recursive approach, the node you invoke this recursive method on, you might even make it a helper method, is going to have to be the node from the top of the stack, right? Otherwise, you're going to be adding the suffix of your word to the root node of your trie, which, while kind of hilarious, is not going to work. So it's a pitfall to be aware of. You've got to invoke this recursively on the correct node. So if I were taking the recursive approach, I'd be writing a recursive helper method to do this, and I would call it on that first node. Okay, so otherwise, I know from find that my node isn't present, my word isn't present in the tree. So I'm not actually going to ask for a child. I am going to inform it that it's getting a child. How am I going to inform it thusly? Well, I've given you this sorted array map class, and it's over here. And it turns out it has a method called add. And so you give it a key and a value. So the key will be a character, and a value is going to be a new trie node. Okay? So I'm going to create some new trie node. Then I'm going to add it to children with the first letter as the key. The first letter is the key. And then I'm going to call t dot, whatever my recursive help is, with the rest of the prefix. So that's what a recursive approach looks like. What about an iterative approach? We've got a promise to keep. So you're going to have an initial current variable, let's call it t for now, which is what was on the top of your path, okay? And now we're again going to have a for loop for each char in the rest of your prefix. So for each character after the ones that have already been taken into account, right? What you're going to do is, much as before for t, we're going to get t's children, and we're going to do an add. So actually, we need another variable here. So I'm going to erase this because I didn't write that much. So I've got some other trie c, which is a new trie. So that's a c for child, just keeping it simple. Then you're going to tell t dot children to add, your key and c. So your key is just the current character that you're exploring in your for loop. And then you're just going to say, you know what, t equals c. That's how I descend through the trie. And then after the for loop ends, we're going to say t dot is member is true. So again, these are both doing exactly the same thing. They're just organized a little bit differently. And those differences in organization, whichever approach is more straightforward for you to grasp is the approach I would encourage you to undertake in your solution. Cool. Any questions? Any questions? All right. Like I said, if you can solidly get add and contains working, I think the rest of it is going to go very, very smoothly. Good. Let's talk about Project 4. Project 4 is going to be really different from our other projects so far, but really a lot of fun, I think. So Project 4 is to build a text adventure engine. So back in the 80s in particular, a really common type of computer game was a text adventure. Graphics back then wasn't exactly what it was now, especially from what I've told you about the CPUs back then. My Commodore 64 with its 1 megahertz CPU wasn't exactly rocking lifelike video. I mean, you could make pretty fun games with it, don't get the wrong idea, but the textual world was dominant when it came to adventure games. Now, what's the underlying rationale for this assignment? I mean, it's sort of a cool and interesting thing to do, but also it's going to help you think in a different way about the idea of a tree. Specifically, you're going to be developing this engine so that it can bring in a configuration file, a description of the adventure. So we've completely separated the code, the programming part, from the this is how my map is laid out for my adventure part. And in processing that data, how the adventure is laid out, which will go in a regular text file that's got a little bit of structure to it, you're going to be basically walking through a tree that corresponds to the data from that text file. So that's how this project relates to the broader picture of things we're looking at. The general idea of a tree is pervasive in data structures, which is one reason we're looking at like 10 different ways to do it. So here is an example script based on the idea of these text adventures. Zork was the best known and most popular. So you're in MC Reynolds 315. Banks of desks stretch southwards and upwards into the gloom. The blackboard broods dark and empty like a giant watchful eye. The door is to the west. There is an eraser here. So now the idea of a text adventure is you type in short phrases that indicate the commands you wish to give. Take eraser, taken. Inventory, you are carrying an eraser. Go west. You are standing at the east end of the hallway on the third floor of MC Reynolds. 315 is to the east, and Dr. Goodrich's office is to the south. The hallway continues to the north and to the west. Go south. You start to go that way, but then change your mind. Now, why did you change your mind? Because the hallway only continues to the north and the west. Go north. You're standing in a hallway on the third floor of MC Reynolds, which extends to the south. To the east is 317. To the north, a doorway. To the west, a bathroom. You go east, you're now in MC Reynolds 317. It's bright and sunny. We raise the blinds. The chalkboard is covered with pictures and writing. It's 8 a.m., not so much. Later in the day, there is a stick of chalk here, as Dr. Grossnickel was looking for before class. And then we can drop the eraser there, and it's dropped. So you're creating this adventure game engine, which reads in a text file containing a description of a world and allows the user to explore it. So you're going to get a lot of practice with the general idea of trees, but also with the concept of a set and a map or dictionary and lists. And it's also going to be pretty good practice in putting together an application that's got several different classes doing different things. Start with the timeline. You've got until the Tuesday before Thanksgiving to complete this. So that's Tuesday, November 26th, if I calculated correctly. Yesterday was the 12th. Yeah. So you got till November the 26th. Now, this project isn't like overwhelmingly difficult as such, but it has a lot of different interacting moving pieces. It cannot be completed the night before. It just can't be done. It's just too much. So to help you, I'm setting an intermediate deadline of a week from tomorrow, next Thursday. The goal of the intermediate deadline is for you to get just enough of the engine working so that you've got a good chance to get it done by that Tuesday, November 26th deadline. So the next section is don't panic. Dr. Yorgi originally created this assignment. This solution ran 500 lines to give you a feel for how big this is going to be. But it's really easy to develop incrementally as long as you get started early and get help when you're stuck. So you're going to use a lot of dictionaries in this assignment. The basic, useful, fast dictionary in Java is the HashMap class, which you can find here. Here's, again, a link directly to the documentation. The key methods for HashMap are get and put. Put associates a key and a value. Get returns a value corresponding to a key. We're going to learn about how hash maps work starting on Friday of this week. But you're more than welcome just to use the library hash map. You don't have to roll your own for this assignment. You'll be doing that for Lab 12, but you don't have to do that for this assignment. So hash set is also pretty handy if you just want to be able to easily add and remove things. For instance, a player inventory hash set can be pretty nice. You're going to need to read the project description really carefully. I highly recommend that you give yourself 10 or 15 minutes today to do that. And I'm going to give you the highlights now, but you really want to find some quiet time today to sit down and read this whole thing carefully so that you can make a plan and think about your strategy for getting this completed. Dr. Yorgi suggests printing it out on paper so that it's a little easier to read all at once, and I think that's a fairly good idea. So, what do we have to do for the project? You have to submit a basic version that can at least read in the world description file, and that file is in a format called YAML. We've got more info about it below. And within that engine, once it's read it in, it needs to keep track of the player's current location and print out a description of the location and allow the user to move around using Go. So this is what you need to have done by a week from tomorrow, is load in the world and let the user wander and tell the user where they are, print out the description of the location. Other things that are basic requirements for what you need to turn in when you're done include the following. Obviously, you have to have that. Then, when the player enters a new location, print out the items that are present. Let the user pick up stuff and put stuff down. Let them look at their inventory. The idea of these adventure games is that the user will pick things, objects up, and take them to target destinations. And when the object is dropped in the target destination, you get points. And so we want the user to be able to see what their score is and increase their score when they get an item to the goal location. Then, we're providing this sort of bare bones third floor of MC Reynolds. Part of the assignment, which is due on the 26th, is to design your own world, creating another YAML file and submit it along with your project. So you're going to create your own adventure description, which in principle, I could even load into somebody else's engine if it's working. So a project that does all of those bits is good enough for a B. You can then enhance it to get an A. We've got ideas for extensions, and you can come up with your own ideas as well. We're providing for you several files to use when putting things together. There's this jar file, which is a Java archive. It's a way to include a library in your program that is a YAML parser. So it'll take the YAML file and it's going to give you a data structure that you can explore that corresponds to it. And then hendrix.yaml is here. So let's glance briefly at what this looks like. How do I want to open? I don't want to look for an app in the store. I want to use Word. Oh, there we go. Or I want to use Notepad++. There we go. I don't need anything from the Windows Store for this. I'll download that later. So this is what the YAML file looks like. Let me make it a little bigger, easier to read. So it's laid out in a form where you've got keys and values just laid out. And the keys represent keys that your engine is going to look for, and the values represent strings that it'll use to populate those concepts or those ideas. So this first object is a location. Its ID tag is MC315. It's got a full name, MC Reynolds 315. Here's a description, then here's like a long description. And so the distinction is when you enter a location for the first time, you would see the long description. When you enter it later times, you would just see the short description. And then it's got exits, west, out, south, and up. And then there are items that are present therein. And then there are these 3 dashes, which means we're looking at a new thing. And so we see the 3 dashes. Here's another location. And this is the back of 315. And among other things, there's a green spiral-bound notebook. It appears to contain someone's physics notes, but there's no name on it. This was definitely not inspired by actual events. So then there's another location, the hallway E3, and so forth. And so then each of these, contains name, description, long description, and then items. We kind of have a nice tree structure here because within items, you again have objects that are placed into a list. And each of these items, again, has fields that describe various properties and aspects of them. And that's the general idea of the file format. Now, just looking at this, I hope that you can easily see how a game designer who doesn't necessarily know anything about programming could easily create a game that's processed by your engine. So one of the big goals here, and a lot of software does this, is to separate out the programming algorithmic aspect from the design aspect so that somebody who's not a programmer can still be creative and make stuff and create things. And setting something like this up is a major goal of this project. So that's what that looks like. Then there are several Java files that you're going to be looking at. There is a direction enum that describes different directions one can go: north, south, east, west, northeast, northwest, southeast, southwest, up, down, in, out. Then there is a verb enum: go, look, take, drop, inventory, score, help, quit. Again, as part of your extensions, you can add to these. You can come up with your own commands and so forth. But these are some basic things we have in place. And then command is a class that parses and represents what the player types. And so it's got a lot of code in place to kind of ignore some noise words and do some just really basic parsing on your behalf. And then Adventure Demo shows how to use Snake YAML to read the YAML file, and basically shows how all of those various pieces work, and shows how you might print items, for example. So we're giving you all of that as useful starting points to work with. And then have a long description of what I just went over with the YAML file, and so forth. So again, you need to read all of this over. Make sure that you understand it, because there's really, oh, oops, I need to change that April 12th date there. Whenever you see April 12th, I thought I hit all the April 12th, but evidently not. Whenever you see April 12th, it really means next Thursday, November 21st. But that April 12th will be on November 21st before you know it. So that's project 4. It's a fair amount of work. There's a little bit of a learning curve, but I think you're really going to have a lot of fun with it and really have something satisfying once you've completed it. Any last questions on that? Okay, on Friday, we're going to start talking about hashing. See you then.